Okay, second video, balancing redox reactions. We're going to deal with the basic solution example. And I'll just say this. This one is, one thing to notice is this one had two reactants, and we split the half reactions based on these two. Here we only have one allotrope of phosphorus sitting here, and what we do is we actually use it twice. So this will be the reactant on both half reactions. There's not a lot of these examples, but they do show up, and when they do show up, you will be glad that you've watched this example, because when you first get a hold of one of these, you're like, well, how do I do this? Well, what's going to happen in the end, what we're going to see is that, let's see, one phosphorus one of the phosphorus molecules will be reduced, and then there's going to be three phosphorus molecules that are going to be oxidized, and that's what's switching the swapping electrons out. Okay, so just a little preview. The other thing to note here is just like the case up here, you know, when you get a hold of one of these, let's say a normal balancing method would say, well, I got to deal with oxygens and hydrogens, and there's no oxygens and hydrogens over here, so you can't just adjust the coefficient and go with it. Well, what you have to remember, in a basic solution, there are oxygens and hydrogens in the form of the hydroxide ion and the water molecule, and these are the ones that are going to balance out this reaction ultimately. Now, to get there, we actually do a little trick, okay? And the little trick is recognizing that the first three steps here? It's the same three steps that we've already done for the acidic solution. And well, what that means is that you are actually going to use protons initially to balance things out, and then in the end you're coming along and you're going to add a certain number of hydroxide ions to, in a sense, neutralize the protons you've added. It's a little peculiar, okay? It doesn't represent chemically what's going on, but at the end of the day, we're going to have a balanced redox reaction. And again, like I said in the last video, this is one of the ways that you can one of the methods that you can use to balance redox reactions. And in my opinion, for whatever it's worth, I think this is one of the simpler ones to use. So let's do that. Let's practice with this. And there's our reaction. And we're going to need a lot more room than that, so let's go to this slide here. And again, you know, I'll jump back to the list every now and then, but not a lot. So the first step, we need to split up the half reactions. Again, like I sort of previewed this, there's only one reactant, so the P4 is going to some of the P4 is going to go to form the PH3, and then some of the phosphorus will go to form the dihydrogen hypophosphate ion. Okay, this guy. Let's work on this one first. I don't know how much room I'm going to need here, so I'm not going to start the other half reaction here. Because, like I said, each half reaction is sort of like its own individual little unit that you work with. So we don't really need to see the second half reaction to start doing this. All right. First thing, we want to balance out everything except hydrogen and oxygen. Do hydrogen and oxygen last. And so I have 4 phosphorus atoms here. I need 4 here. That means I'm changing the coefficient in front here. The next step is, well, just like with the acidic solution, you do oxygens first and then hydrogen. So let's do that. If we want to balance out the oxygens, we don't have to worry about it. There are no oxygens here. So go to the next step, hydrogens. 3 times 4, there's 12 on this side, so I need 12 protons there. So I paused the video, shifted that around, it jumped on you. That's what happened. It's not unusual to use a lot of paper or real estate to do one of these. So anyway, I needed to adjust my positioning on the screen. Okay, so now we're ready. We have the hydrogens balanced. We have the phosphorus atoms balanced. But if I'm looking at this isn't a basic solution. This is an acidic solution. I have protons floating around. I want to get rid of those protons, and I will jump back to the set of rules on this one. And all right, it's the most, or the one that's different here is right. Therefore, that's different. Everything else is the same as up there. And what it's telling me to do is I need to add the same number of hydroxides on both sides of the equation. What does that look like? Well, that number is based on how many protons I have sitting here. So, if I want to neutralize this acidic solution, then I'm going to need 12 hydroxides to come along and essentially react with those 12 protons. I can't just do that. I also need to do this. Think about this as almost like a mathematical equation. In algebra, when you're rearranging an expression, anything you do to one side of the expression, you do to the same side you do the same thing to the other side of the expression, and you're doing that here. And by doing that, you keep the atoms balanced, right? We're balancing the atoms first, and then we're bringing electrons in to balance out the charge. So the atoms are balanced in this formula. Now I can actually simplify this a bit and say there's 12 water molecules. Now if I look at my sequence here, I'm like, well, this is in a basic solution, water and hydroxide. I'm good to go now. So again, the trick that we do, we balance it just like we do for an acidic solution, and then we bring hydroxides in to cancel out however many protons we use. Again, in my opinion, I think this is the simplest way to approach redox reactions. Now, since the atoms are balanced now I can go back in and we use electrons to balance charge. And what I'm going to need 12 electrons on this side. Again, don't get caught up in these large numbers. These numbers oftentimes are larger than what we're used to in a typical metathesis reaction. Probably the only thing comparable were the combustion reactions that you probably balanced in Gen Chem 1. Some of those would go up to, in the 20s. It's reasonably common for a redox reaction. And everything is charged, right? So there's a minus 12 charge total here. There's a minus 12 charge total here. First internal check, this is my GER. That's my reduction reaction. It's gaining electrons. That means that the next one that I do better be the oxidation reaction. So again, P4 is the only game in town, right, for the reactant side, so that I'm going to use it. And again, all it's saying is that there's a certain number of phosphorus molecules that are going to do this, and there's a certain number of phosphorus molecules that's going to do that. Same deal. We want to balance up in this case, the phosphorus atoms. There's 4 here. I need 4 in front there. Right? You do those before you do oxygens and hydrogens, and then oxygens first, and then hydrogen second. Do that each time. So I have a total of what? 2 times 4, that's 8 oxygens. So 8 water molecules are needed there. Protons, actually, I think it'll be simpler if we just count them up. So there's 16 hydrogens on this side, and on this side, well, 2 times, okay, that's fine, okay, so 8 hydrogens on that side. So if I want to, I'm using H plus to balance out the hydrogens, and I need to increase the number here, H plus. Next step, I bring in a certain number of hydroxides. Let's go back to purple just to keep it consistent. We're using hydroxides to balance that not to make it a basic solution in some sense. We want to get rid of those protons that we just added. Right? The first set of rules there is just a little trick we're doing to get to, the final step with, relative ease for these things. Whatever I do on one side, I want to do the same on the other side. And I pause for a minute. I say, okay, well, these are going to come together to form 8 water molecules. And what do you know? And this honestly is, you'll see in examples that you do this. I mean, there's 8 water molecules here. There's 8 water molecules here. Let's go ahead and cancel those out. We don't need them. Anything that shows up on one side and the other side, you can start canceling out here. It simplifies the process along the way. Now let's look at the overall charge. And remember, it's only electrons that we can use to balance out the charge. There is a -8 charge here, and there is a -4. -1 times 4. There's a -4 here, so I need +4 electrons there. Perfect. That's my Leo. My Leo. For every Ger, there's a Leo. So this guy is donating the electrons. This one is accepting the electrons. We're almost there. If we paused, if we counted up the charge, if we counted up the atoms for each of these individually, everything's in balance. It's very messy, but that's fine. That's what redox reactions are all about. Let me go back, just remind you of the next step. And now I want to balance the number of electrons that are transferring between the half reactions. I have 4 here, 12 here. I'm looking for a way to balance all that out. I need to multiply this half reaction by 3. And let me just go ahead and do that. So 8 times 3, that's going to give us 24 hydroxides. There's no waters. There's going to be 3 phosphorus molecules there. There's going to be 12 of the ion. And then finally, like we were wanting, 12 electrons in this transfer. I'm going to scribble this out just to remind myself that I have taken care of that. And we are almost there. Let me go through and just see if there's anything I can. Yes, I can cancel some things out. And it's usually hydroxides and waters that you're canceling out. Those things that you added, you start canceling out at this stage. Notice, again, you can think about this as our little dividing line. Anything on this side can cancel out with anything on that side. Well, notice I have 12 hydroxides here. I can get rid of 12, half of the 24 hydroxides are going to cancel out. And then that's it. There's nothing else in common. I guess I can go ahead and officially cancel out the electrons. They don't show up in the overall reaction at the end anyway, but anyway, let's bring everything together. And yeah, I'm just going to say 4 P4 molecules. And what do we have? 12 water molecules, and we have 12 hydroxide ions. That's the only things here, right? Again, sometimes it gets messy, so just make sure you can, not paying attention to what I'm doing, just make sure that you, add everything else up correctly. That's H3 plus our 12 ions, and yeah, that's the only thing over here, 2PO2 negative. Yeah, there's nothing else. Everything else canceled out here, so it's nice and clean on this side. And everything should be balanced. Charges, there's negative 12 here. There's negative 12 here. That's good. There's 4 phosphorus. I'm sorry, 16. There's 16. 4 times 4, 16. 12 phosphorus here, and then 4 here. That's 16, so that's good. Hydrogens, there's a bunch of them. There's 24 here, and another 12, what, 36? And you do have 36 hydrogens here as well. There's 24 hydrogens plus 12 more. Okay, that's enough. That's enough of a count. I think oxygens would do fine as well. This is a balanced equation. But again, what you see is that these numbers can really balloon on you, and it's fine. Everything is balanced out, and you're in good shape here. Actually, I do see one other thing that we could do to clean this up a little bit more. We could factor out a 4 all the way through this expression if we wanted to. Now, honestly, on a test, if you got this far, you're fine, okay? Something like mastering chemistry, it may be picky enough to where it may want to see this kind of equation where you do the lowest common multiples, I guess is what I'm looking for here, and then 4H2PO2. And I think that should be balanced. But yeah, that is a lot cleaner. So again, on the test that would be fine up here, but anyway. Let's just go through oxidation numbers real quick, just as a little reminder of that little game. And so phosphorus, that is one of the elemental forms for phosphorus. Phosphorus, I think, has 4 different allotropes, I believe. 2 common, 2 a little less common, but they're all, if it's just phosphorus, no matter how many phosphorus atoms are joined together and what they look like, we treat that as a 0 value with respect to oxidation number. And then if we look over here, the oxidation number here is going to be a minus 3. Right? That phosphorus, minus 3, is going to balance out with the plus 3 from the 3 hydrogens. So it's an overall oxidation number, sum of oxidation numbers of 0. Right? And then let's do the oxidation number over here. So the sum of the oxidation numbers, we need to add them to equal, let's say, all of these have to add up to equal -1, right? Overall charge. Each oxygen is carrying a -2, there's 2 of those, so it's contributing a -4. Overall phosphorus is going to be some number, which is yet to be determined. And then hydrogen, each hydrogen is +1, there's 2 of those, so there's a +2. So the phosphorus has to be carrying a +1. So +1 + 3 -4 would give us a -1. So this oxidation number is a +1, which is what we're wanting. Let's see. 3 of the phosphorus get converted over to this thing. So 3 of the phosphorus is going from 0 to the -1. Now, they are, or +1. That's the one that's being oxidized, right? It's loss of electrons right here. And then when the phosphorus is going to the phosphine here, then what we have is oxidation change of 0 to -3. The number is reducing. The compound, the atom, the molecule is being reduced. It's right. It's gaining electrons, so that's consistent. And yeah, that's a complete set of reactions there. And phosphorus, it's acting both as the oxidizing and reducing agent in this particular example. And again, there's a few of these where you see this, where there's only a single reactant, and that single reactant shows up as the reactant in both half reactions. Okay, that's it.